All right. So the question says that in an experiment where the diffusion coefficient of acetone is to be determined, a proportional controller is used to control the temperature of acetone within that particular range, right? 30 to 50 degrees, right? Temperature control is achieved by means of an electric heater whose power is adjusted by the controller. The controller is adjusted so that the power output goes from 0 to 100% as the measured temperature goes from 45 to 35 degrees Celsius. If the set point is kept constant, find the following. So the first question that you had to answer was to find the proportional band, right? There's a formula that you guys already have for finding the proportional band, right? So there you just had to say PB. Let me use red. So you just have to go there and say PB is equal to the temperature that you are dealing with, right? 45 to 45, right? I mean, 45 to 35, which is your temperature change, right? The actual temperature change that we have here. So it's 45. It's 45 minus 35 divided by the actual range now, which is 50 minus 30. Do we all get that? Those who are here? All right, I'm just,
Yes.
Okay, perfect. So from there, you also multiply it by hundreds, right? So that you can get it in percentage, because remember, even from your notes, I'm guessing that is there that the proportional band is always presented or represented with percentage, right? In percentage form, not fractional form, right? So you also need to multiply it by 100 to make it a percentage. And from there, it's 45 minus 35 over 50 minus 30. Multiply by 100, which gives you 50, right? I hope that we are all following so far. So that gives you 50. That is the value of your proportional band there that you had to calculate, right? So another question that you had was for you to find the proportional gain, right? So there, under the proportional gain, you guys are saying that you already have a formula that was given to you for calculating KP, right? So if you could look at it, KP, you've got many formulas that you can calculate it. You can calculate KP from a lot of variables that you deal with in process control. But so far, you guys, they gave you a formula that you can calculate KP from error, right? And also from the change between the desired and the actual output that you get from your process, right? But simply enough, for this question, you wouldn't need to do that because you don't even the information. I mean, you don't even have the information that you could use if you were doing things that way, right? So in that manner, you now go and opt for a formula where you will need to say Kp is equals to 100 over the P, right? If you are following, there are reactions there on the chat box, I think, that you could use to show that we are together here. Okay, so this is the formula that you use. So with regards to other people were asking, why do we now come and say it's equals to 100 over 50, right? Instead of saying 50%, right? And I told them that just like they said in your notes, right? Which I'm hoping they did, or which I believe they did. KP, PB is always represented in percentage, right? Simply means that you always take that value, the percentage value that you calculated as it is, not to say 50 over 100, right? So you always come and put that value as it is. It's 50 as it is, not 50%, because that is going to be 1/2. That is going to be, 50%. That's going to be 0.5. And that is not what you are looking for. But you put 50 as it is, right? I hope you guys hear me with this one, because you could lose a lot there if you go and just put 50%. All right. So in that regard, you go there and then your answer is going to be 2, right? There are some relationships between your K and your, there is a specific relationship that says when K or the gain is closer to 1, this is happening. And when the gain is greater than 1, this is happening, right? Okay. So there was another question that was always raised here. Okay, as I was saying, that there was another question that was also raised here by some people to ask, what is the significance of the proportional band, right? So in class, when I explained after class, for those who stayed behind while I was to consult, so we looked at what the aim of the proportional band is, right? Please, if you just got here, mute yourself. All right, I was explaining that it links to the sensitivity of your controller, right? And it also helps you to establish stable control under different process conditions, right? Because for the same calculation of PB, let's look at a context where you'll have your PB and you find that the range now, the temperature change that you have is no longer 45 to 35, but let's say it's 45 to 40, right? Divided by the same range that your sensor can handle, right? 30. And then let's look at the value that we find here for our PB. The value that we find here is 20%, right? And with that 20%, and you were going to calculate the gain, your gain was going to be higher than the gain that you got before. Anyway, just to explain this, let me link it to the importance of proportional band, right? So you can see something is happening there, right? And you can see that there should be a relationship that we establish, right? So the relationship that is there is that your proportional band and your sensitivity, the sensitivity of your controller, they are inversely proportional, right? Which simply means that if you have a higher proportional band, then simply means that the sensitivity of your controller is low, right? And if you have a lower proportional band, simply means that you have got a higher sensitivity. So let's look at it in this way. For the PB that I just made an example with here, we have got a lower PB. Simply means that we have got a higher sensitivity. So practically, this is true because we are dealing with the temperature change or the change that is very much close to each other, right? 45 and 40, they are very much close to each other. So when you are dealing with that small temperature change or a smaller temperature change, your system now, or let me just say your controller becomes more sensitive as compared to when you are dealing with a larger temperature change or whatever change in your controlled variable. Are we all following so far? Yes, we should, right? Or do we have any questions on that? A, B, C? Let's talk, right? This is not a class where you guys just hide and not talk, but let's talk here if you've got any questions. Can we? Guys?
Yes, sir, we follow.
Okay, because you're the one who needs to tell me what's going on with you guys, right? To tell me what you want done, because I don't know. You're the one who need to do that. So the question. Okay.
So the significance is that it links to the sensitivity of the controller only.
So in words, right? The significance is that this is a parameter that you adjust, right, in order for you to obtain stable control under different process conditions, right? So I can write it in words to say this is a parameter that you adjust in order to control, or to obtain stable control under different process conditions. Different process conditions are talking about those temperature changes that you're getting there, smaller or large, right? Such that, or you can write it in your own words now, such that the higher the PB, the lower the of your controller. I hope you get that. So that is just the basic significance, right? That should be able to give you, that should be able to have you stand on good grounds, right? Do you have any questions again on that?
Okay, so thank you.
All right, perfect, no problem. If we don't have any questions on that, then we move, right? You don't need to worry about this one. You guys, you're saying you didn't do it, so it's cool. 3.1 is not something that we are going to look at, because you guys have that on your slide. All right, another thing that is worth talking about, right? 3.2, do we all agree that it was worth talking about? Yes, right? I don't even have to ask, because a lot of people have been reaching out about it. So cold junction temperature compensation, right? So you know that in your thermocouple, for example, you have your hot junction, your reference junction, your cold junction, right? I mean, if you're just putting it in words, right? I'll wait until somebody says, yeah.
Yes, sir.
All right, perfect. So there's something that is called cold junction temperature compensation, right? So when you are measuring your temperature using a thermocouple, can you please mute yourself? Oh, okay. When we are measuring the temperature using a thermocouple, right? You have got a cold junction, right? Which, when you are doing this type of stuff, which is called cold temperature, cold junction temperature compensation, your cold junction is actually referred to also as your reference temperature, right? That's how you roll when you're doing that. But what is this? What is this cold junction temperature compensation? Okay, I didn't get an answer from anyone before, so I'm not surprised that I'm not getting it now, right? So this is the method where you make temperature adjustment, right? To account for, maybe let me say, to account for the temperature difference between 2 points in your thermocouple circuit, right? I know when I just put it like that, it sounds so long, like it's far-fetched in a way, it's not understandable. So basically, we are saying that you've got your cold junction, right? Which is your, your junction that have got the lowest temperature, if we're talking about your thermocouple. And you also have got a hot junction, right? So you look at the stuff that you are trying to measure, the temperature that you are trying to measure. Generally, they say that the temperature that you are trying to measure is always much closer to the temperature of the cold junction as opposed to being much closer to the temperature of the hot junction, right? So I'm saying that if my thermocouple, for example, depending on which type it is good at measuring temperatures between 20 degrees and 50 degrees, right? I don't know if this example that I'm trying to make will work, but basically what I'm saying is the temperature that you're trying to measure, let's say you're trying to measure 23, right? It will be much closer. I mean, according to the principle that led people to trying to do this cold junction temperature compensation, to be much closer to the temperature of your what? Of your cold junction. So what happens now is they go and do something called cold junction temperature compensation. And basically what they do is they adjust the temperature of the cold junction to be closer to the temperature that they're trying to measure. And this is not something that you carry out manually this time in life, right? At this age, now it's done automatically, right? So there might be a formula that is guiding that cold junction temperature compensation. But what they do actually in words, right? Because that is what you're looking for, that's why you're here. You're just adjusting the temperature measurements to account for the temperature difference that you could get between 2 points in your thermocouple circuit. Or even if it's not a thermocouple, because you don't only carry this out in a thermocouple. If you've got any follow-up questions on this, I'll take them now.
Sorry, sir. You say if it's 23 degrees Celsius, they're going to adjust the cold junction in such a way that the temperature of it is closer to 23 degrees Celsius, or?
Yes, they will do that. And when they do that, you will find that it will make your measurements now more accurate, right? Because your cold junction temperature is closer to the temperature of your what? Of the stuff that you're measuring, right?
All right, okay.
So the purpose is for you to get reliable and more accurate measurements. That is just the purpose, because if the temperature of your cold junction is much far from that of what you're measuring, it has been proven that you get measurements that are not accurate. So they do this compensation. They bring the cold junction closer to what you are measuring, and then that's how you make them more accurate. Are we good? Hello?
Yes.
All right, perfect. You know, I won't continue unless I hear somebody say we good. Okay. What's happening in the chats? Nothing, huh? All right, nothing is happening in the chats. Cool. All right. Another question that we had was 3.3, right? We are dealing with a lot of stuff that you cannot afford to miss. So 3.3. So it says that consider a K-type thermocouple, right? So a K-type thermocouple, I've got these two materials, chromel and alumel, right? With a hot junction at 50 degrees Celsius and the reference junction at 10 degrees Celsius. And they ask you what is the polarity of each material, and you are asked to justify your answer. So somebody asked me this question after class, and I didn't want to answer it, or I said I'll get back to them, or we'll do it here. I think I said we'll do it here. That was because the answer is not as straightforward as you think, right? That was because the answer needs to lead back to what chromel and alumel are, right? So let's look at these two material, right? They say it's a K-type thermocouple. Even if you can do a Google search of a K-type thermocouple, you'll get the two material that it's made of, right? Chromel, right? So these two materials are alloys, right? So there's chromel and there's also aluminium. So both of these materials are alloys. Alloys just simply means that it's a mixture of metals in a way, right? Various metals combined to form one piece with its unique properties, right? So if you're just talking about the theory of it, you know that aluminium, right? The second one, because the thermocouple, you remember your thermocouple Seebeck effect, two dissimilar metals, what? But these ones here are not pure metals in a K-type thermocouple. They are metals, but they're alloys, right? They are metal alloys. So on this one here, where you have got polymer, right? It's a mixture that have got nickel, aluminum, and also a chromium in it, right? So chromium, of course, is one that is only of nickel and chromium, right? Chromium and also nickel form this alloy here. So you say that with the hot junction at 50 degrees Celsius and the reference temperature at 10 degrees Celsius. So look at these temperatures here. For the first one, this is a very standard situation that you'll get when you're dealing with this kind of stuff, right? It's a very common situation because your reference junction is lower than your hot junction, right? This is something that we expect to see, right? It's very normal, right? Hot junction at 50 degrees and the reference junction at 10 degrees, right? If you didn't do this on your lecture units for this semester, then it didn't deserve to be here because this just formed part of our last year's test, right? Okay, so you're asked now, what is the polarity? You also need to understand what polarity is. It was assumed that you guys know what polarity is from your chemistry and whatever way there where you mentioned polarity, right? So polarity, we're talking about the charge, right? The charge of your material. When you ask what is the polarity of each material, you want to tell us the charge of chromium in this case and the charge of alumel in this case. So you'll go there and tell us if chromium is positive or negative, or if alumel is the one that is negative or the one that is positive, right? And then you also need to justify, right? And how do you justify these? You had to understand the concept of the Seebeck coefficient, right? You had to understand the concept of the Seebeck coefficient. The fact that alumel, right? You have got a lower Seebeck coefficient as opposed to chromium, right? Okay. That is not the answer yet. That is not the answer yet. It's just part of the theory that forms the answer. All right, so the polarity of each material. Now that we understand that alumel have got a lower Seebeck coefficient as opposed to chromium, right? Which makes it to be a material that will produce less voltage when exposed to a certain delta T temperature difference, right? So in this case, what will happen? Because you also need to look at there's this concept of electrons, right? You guys are more familiar with that. Electrons moving from hot to cold, right? Okay. Let's find if you can have your answer in words. So if you can look at the hot junction, it have got a higher temperature than the cold junction, right? So in this case, based on the Seebeck coefficient of chromium that is higher than that of alumel, right? So in this case, chromium displaces less electrons towards the reference junction, right? So this is going to be worth maybe you doing maybe a small research on it, because this only doesn't cut it, right? If you want to understand more about it. So chromium displaces less electrons towards the reference junction, right? As compared to alumel. And you know that when electrons move from a particular area to another area, you know that the concentration of electrons on the other area where they are moving to will be higher, and electrons are negatively charged, right? Which simply means that where they are going to is going to be negatively charged, and where they are moving from is going to be positively charged. So that's why in this case, you'll find that chromium is going to be what? Positively charged, right? Because it have got, I mean, based on that Seebeck coefficient and how the electrons move and how much voltage it induces when it's exposed to temperature difference, and alumel will be negative. So this is just going to be a standard situation that you get. But if you guys didn't have these on your slides, or you were not taught this, maybe it's time now that you page on your slides to find out if you have this stuff or not, and make a final judgment, right? So we make a change now. If the hot junction of the same thermocouple is kept at 50 degrees, Celsius, but the reference junction is now at 80 degrees. You see now the reference junction for this scenario now is higher than the hot junction, right? The hot junction is at 50 and the reference junction is at 80. What would happen to the polarity of each material? Of course, it will change and be the opposite, right? Because the electrons are also moving in the opposite direction, or in contrast to what would be expected in a standard situation where you have got your reference junction at a lower temperature than the hot junction, right? Temperature, right? And the Seebeck coefficient of your materials are aligned like that in terms of which one is lower and which one is higher. I hope we are good on that one, eh? Are we good? Because it's theory. If you don't understand it from me, you might understand it better from another source, right? But do stick around if you are not getting it. Maybe we can provide you with more stuff to learn from about this particular concept. All right, because time is an issue here. We should dive now into what has been a source of attention, right? Here now we're talking about 3.4. So I think this one now deserves all the time that we have. So you've got something going on there on 3.4. Let me share my screen and share the question. Now, if you still need, if you want more literature on understanding what is happening with 3.3, come through. Then I'll just share it with you. You'll read and tell me what you don't understand. Or I can just share it in the group for everyone to see. All right, so 3.4, a lot of stuff is happening there. They tell you that a voltage of 23.72, right? Hey, a lot of people are waiting in the waiting room. Didn't see them. All right. So they tell you that a voltage of 23.72 millivolts is measured with a type K thermocouple at 0 degrees Celsius reference. And then you are told to find the temperature of the measurement junction, right? The temperature of the measurement junction. So the measurement junction, you have read quite some stuff here, the measurement junction, the sensing junction. So from literature or just from the standard image or the schematic of a thermocouple, you'll understand that the temperature that you get at the measurement junction is typically higher.
Sir,
Yes.
sir, we
Yeah.
have 3.4 in our lecture note. The answer is there. Can we move to 3.5? Oh,
it's okay. I'm doing this so that I can show those of you who don't understand how to use the data table. Right? I'm not doing this to show you how to answer the question, but it's gonna lead me well to the table.
Okay.
All right. So you are given that particular voltage being measured with a thermocouple at 0 degrees reference. So keep the reference in your mind, right? And then you are told that to find the temperature at the measurement junction. Like I was saying, the measurement junction, the temperature that you get there is typically higher than the one that you'll get at the sensing junction, as written here, because the measurement junction is much closer to your heat source, right? Or to the object whose temperature you're trying to measure. Anyway, that is just a concept or a theory, right? And then let's go now to the diagram and find out how do you now find that particular temperature, right? Okay. So we are going to a K-type, right? A K-type is this particular one here. So I'm sure you guys are more familiar with the diagram now, since it's not a biggie, right? But read the title of the diagram, reference junction at 0 degrees Celsius, right? That is the reference junction. If a question comes and tells you that the reference is at 25 or 50 or whatever temperature that falls within this K-type thermocouple, then you will need to act accordingly. And I will tell you how, or show you how to act accordingly when we do the other question that follows after this one. All right. So the table itself is like this, right? Thermoelectric voltage in millivolts, right? If you can look at the first column on the left, which is this one, right? And the first row, these two are representing temperature, right? Just hope we are following there and no one is left behind. These two are representing temperature. So this one here is your major scale, right? Your major scale. And this one here on row 1, these are increments, right? Of 0 to 10. So basically what I'm saying is this is 450 and the other one is 460, right? And you ask yourself, what if I want 455, 455, right? These increments are there for that. The one on row 1, on the first row, because this one here will be 450 plus 1, right? Which will be 451. So 451 is represented what? Here, right? And 452 is here. 453 is this one. Do you get it? That's why mostly you will find that it doesn't have this last column. It's not necessary because it's repeated, right? Because they wrote 10, right? They also gave you 460. Do you get it? Because if you've got 450 plus 10, it gives you 460. That's why you find this reading here the same as this reading here, because this is 460 and that one is 450 plus 10. Do you get it? So that's why for other tables, you'll find that they end at 9 because it's like 459. And then the next one will be 460 that comes from the major scale. If you don't understand, please talk now or forever hold your peace. Are we good? We all good, right? So if we say go and find 432, I mean, let's say 532. Of course, you know, this is 530. And based on increments, 2 is there. Then this is 532 here. Do you get it? All right. I'm gonna assume that we are together on this one. All right. So the question asked you now, you said you know how to answer the question. If you don't know how to answer the question, please say it now before we move to the next one. Okay. So everybody's good with this one, huh? Because it's there on your slides, you say. All right. So
Sir, can we please just go over it?
okay, perfect. I'll do that just to make sure that we are all good. So the reference temperature is at 0 degrees, right? And your table is already at the reference of 0 degrees, right? So this matches. What you need to do is just go and pick the value of temperature that you get at 23.72 millivolts. Let's try to see that and see if it will work, all right? At 23.72 millivolts. Okay. So on the K-type, we are here, 23.72. We look around, right? You look around to see where you might find it. And it was 23.72, right? Let's look around, 23 points. And we find that it's between this one, right? And this one, right? You get it?
Yes.
So what is this one? The first one is 23.714 millivolts. That is going with 572 degrees Celsius, right? Let me just put a table here so that you understand it better. Okay. Just gonna put a table there with some nice lines. because you're going to be doing some interpolations, right? Because already you saw that it's not there. So it will need to be interpolated, right? So as you can see, you're going to have 1, you're going to have 2, you're going to have 3. The first one was your 23.714, that is going with 572. We all agree, right? And the one that you're going to have here is the one that you're trying to measure. You're going to have 23.72, of which the temperature you don't know, right? So this temperature here, we're going to call it Y2 based on our interpolation equation, right? So the next one, the second point, or the third point, because the second one is the one that you don't know. The third point is the one that I've got 23.757, and the temperature is 573, right? If you look at this here and that, right? Are we good? And then what you do now is just to write your interpolation equation, linear interpolation, right? To find what Y2 is. So you go there and write Y2 is equals to X2 minus X1. And then this is Y2 minus Y1 over X3 minus X1 plus what? Plus your Y1. Your Y1, which is your known temperature, right? So you just substitute those there, you should find the answer, right? We all should know the formula for linear interpolation, right? Do we all know that?
Yes.
Yes.
So it's gonna look good if you even write this table there while you're interpolating to show that your stuff is proper, so that you don't also make mistakes when you punch in your stuff, right? You can have the table and then you just substitute. If you don't know what how linear interpolation goes, that should be another task that you embark on. All right, so we are all good with the table before we move to the next question. Okay, nobody's saying anything, so we are all good. We clear that. We move to the next question, where a voltage of 3444, right, millivolts is measured with a type S thermocouple with 25 degrees Celsius reference temperature. So this is just one of those questions, right? I think somebody asked me this after class, and I didn't give them a straight answer, because also different tables have got different reference temperatures. So the procedure, the overall procedure is the same, but you might need to do something different, right? Just because your reference temperature is now different. All right. So okay, there's no one who wants to enter. Okay, so how do you now go and do this? So you measure this at with the reference temperature of 25, right? So this is what you measured when your reference temperature was what? Was 25, right? So find the temperature at the sensing junction, right? I hope you guys are following and won't be lost on this one. You measured this when your reference temperature was 25, right? And you need to measure the temperature, or find the temperature at the sensing junction. If you had a table that had a reference temperature of 25, right? It was going to be a standard procedure that you do, right? But our data table is not for 25 reference temperature, 25 degrees of reference temperature, right? It's not that. Ours is 0 degrees, right? Which simply means that when we go now to our table, the one that we use, our voltage output is going to be different, right? So how do we find the actual voltage output that we have here, right? You go to the voltage output that they have at 25 degrees. Please, I see someone, please mute yourself. you go to your type S thermocouple and find the voltage output at 25 degrees, right? Type S at 25 degrees, right? Type S, 20, 1, 2, 3, 4, 5 at 25 is this one, 0.143, right? So that's the output that you get 0.143 before I forget it. Okay, at 25 degrees on a data table that is at 0 degrees reference temperature, right? You get 0.143, right? This is going to give your new voltage output, right? The voltage that you measured, right? The V is now going to be this one plus the one that you measured at 25 reference temperature, which was 3.444. And now having the answer that you get here, you can use this answer to what? To answer with the standard procedure, but now using a table that is at 0 degrees reference temperature. Hey, are we all together on this one?
Sir, please go over that again.
Okay. Okay. Yeah, this deserves to be talked about, right? So if you look at the data table that we have, like even the title, the reference temperature is what? Is 0, right? So if even on this question here, the reference temperature was 0, you were just gonna go and find the temperature at 34444, right? And if you have to interpolate, you just interpolate just like we did on the first question, right? But that is not the case here, because the reference temperature of this voltage output that they gave us is what? Is on the basis of 25 degrees reference temperature, right? Simply means that if we had a table that was that had a data on 25 degrees reference temperature, we were just gonna do the standard calculations, right? The way we do, right? But we do not have that table. Our table, the one we have for our data, is at what? Is at 0 degrees, right? Reference temperature, right? So this simply means that for you to go now and use that table, right? Your voltage needs to be one that is found from a table that have got 0 degrees reference temperature, right? This one have got 25, right? It simply means that you go there and say the voltage now that you're going to use, if you're going to use the table that is on your appendix, is going to be the V at 25 degrees, right? On 0 degrees reference, right? Plus the V measured at 25 degrees reference. So even if, for example, they say that type S thermocouple with 50 degrees reference temperature, what you had to do was going to take the voltage that you get at 50 and add it to the voltage that you are given here, the one that they tell you that it was measured at 50, right? This is the only difference. This is the only tricky part here. The voltage. You add. So you go to your table that you have that is at 0 degrees Celsius reference temperature, and you go to 25 degrees and find the voltage at 25 degrees on that particular table. And then you add that one to the one that was measured at the temperature that they gave you. Are we good? Okay. Nobody's saying anything. It means we are good. Okay, anyway. We are good.
Yes, we are following.
All right. So after getting the voltage, then you continue with your standard procedure, right? You added those 0.143, right? Plus 3.444. So to see if you are able to do this, just go and change that reference temperature and make it any temperature that works there. Just make sure that it is a good temperature that you can pick the value from directly from the table, right? So that you don't interpolate twice. So what is the value that you get there? 0.143, 0.143 plus 3.444. You get 3.587, right?
Yes, sir.
So this is now just going to be the voltage that you do the standard procedure on. You're just going to find out on your 0 degrees reference temperature table, right? Or junction. So you're just going to use this and do the same thing that we did for 3.4. At what temperature do you find this? That is all. Is it good?
Yes, sir.
If it's not good and you don't want to talk, you can send something there on the chat, eh? You can send something on the chat and then we find out what's really going on. If there's nothing, then let's see. All right. The calibration of an instrument is to be checked at that particular temperature there. This temperature is measured with the type J thermocouple with 0 degrees reference temperature. Calculate the millivolts expected there. This is just the same thing, right? Picking from the table, right? They gave you the temperature, right? And from the temperature, you need to find the volts, as opposed to what we've been doing with 3.4 and 3.5. Just that now your Y2 is your voltage, right? Simply means that when you write your table, you write it accordingly. And your X now is going to be your the stuff that you know is going to be the stuff the temperature. Are we good, or you want us to walk through it? Okay, I guess we are good. Since nobody's saying anything, come on, guys, you don't have anything to fear here. You don't have anything to fear. Okay, we good. All right, great stuff. Great stuff. Okay, not good. Why not good? Why not good, Nolo? What's happening? Because you guys are just saying not good, but why not good? Because you need to understand where things are going wrong, and then we try to fix them. For theory, just make sure that you understand the stuff that you're dealing with, because process control theory is not one to be crammed, right? Next year, when you do process control, we're going to assume that you know, right? We are going to assume that you know these things. So there won't be an excuse. All right, anyway, somebody wants me to refresh on 3.5, right? In terms of which one is going to be X, which one is going to be Y, right? So, okay. So let's say I'm just gonna assume the values here because I don't want to be scrolling back and forth with the table, right? Let's say they told you that I mean you've already found your 3.5, right? You said 3.5, not 3.6. All right. This one is for 3.6 with regards to X and Y. So I'm just saying that they gave you the temperature there, right? Which simply means that your temperature is going to be something that is known, right? Which is going to be 2. Let's say it's between 272 and 273, right? Because it's 272.8, right? And your Y, I mean, this is going to be your your X because you know all the things about it, right? Your Y is one where you don't know the Y2, the one that is here. You get it? The one that you don't know is going to be your Y. Y is going to be always your unknown for all of these things. Or you can write it like that, or you can write it the same way, but you will need to solve for Y now. You will need to do some algebra to solve for Y, right? It's not confusing. It's just that it might be a bit longer. So here you just write the one that this one is between. Let's say it's between 3.4. Sorry, not this one. We are here on 3.6. You don't have anything here, right? So you just go and look at the ones that this is between. Let's just say it's between 2.4 and 2.6. I'm just guessing because I don't want to be scrolling down there, right? Do you get it? Yeah. These are just the millivolts that are accompanying those temperatures that you found your given temperatures to be between, right? You know that at 273, let's say your millivolts are 2.6, you just write it like that. At 272, your millivolts are 2.4. Just write it. I just guessed them because I don't want to be scrolling back and forth. But I just hope that you understand that your Y2, you're just going to write your formula, and then you just substitute it from this table. All right?
Yes.
Okay. So refreshing on 3.5, I said you're going to have a new voltage that you're going to use for your calculation. And this V is going to be your V at the given reference temperature, right? It is always like this, just that for your common stuff, even if you're saying the V is the V at your given temperature, right? Okay, the V at the given temperature is 25 plus the V that is given at 25 reference, right? 25 is not always the case. It depends on the question, right? If it's 50, it's 50, right? So for rule of thumb, I just want you to know that it's always V, and then you take the one at the reference temperature that you are given, and then you add it to the one that you are given. And then from this new V, you can work with it on your table that is at 0 degrees reference temperature. Because if you can look at all your tables, let me just scroll down to show you what I'm talking about. You see your tables here is at 0 degrees reference temperature. I think all your tables here, 0 degrees, right? So you can just take a value that was found from 25 degrees reference temperature and use it on this table. Your volts first need to be adjusted, right? To be the one that fit this 0 degree reference temperature table, right? Do you get it?
Yes, we get you, sir.
Yeah. So always, you always need to adjust, whether it's 50 degrees or 60 degrees. If your reference temperature is not 0 degrees, just know that you need to adjust before you continue. If you just continue, it's going to be incorrect. Are we good? Guys, are we good? I'm just hoping we are, right? Okay. Seems like now we can take for the next 7 minutes or so before the meeting. Go back to 3.3, okay? What is happening on 3.3? Hey, okay. We have been talking about this. Where were you? Where were you? Where were you? We've been talking about this. Oh,
Well,
you joined late.
yeah, load shedding disturbed us.
Okay. I said just link your knowledge of the Seebeck. Okay, maybe this is something that you should do as you study, right? Go and find out electron movement between two different materials in you can search any type of thermocouple, K type, S type, J type, right? You can search any, and then look at the polarity of the materials. It's always there if you're focusing at the understanding of the thermocouples themselves, right? But the general answer that I gave there was that you need to say that your aluminum have got a lower Seebeck coefficient than chromium, right? And for a system where the temperature of the hot junction is higher than the reference temperature, then chromium will be positive and aluminum will be negative. But if you want to supplement that with some deep theory that is correct, you can also do that. Because I think like this is one concept that is bringing a lot of confusion for you guys. But if it happens that the opposite happens, with regards to the temperatures being higher than one another, then of course also the flow of electrons will be opposite, right? Because it's from hot to cold, regardless of whether it's a hot junction or cold junction. But as long as the temperature is higher, then electrons will move from the higher one to the lower one. And then at that point, that's why the electron movement will also be opposite, now making your aluminum positive and your chromium negative. So just go and look into that now, because we can discuss this one the whole night, I think. All right, great stuff. Anything to talk about? Anything else going on? Okay, it doesn't look like anything is going on. We have got like 4 minutes remaining here before we disappear. And you guys don't want to say anything. What seems to be the problem? Guys?
There's no problem.
Mr. Wonga. I don't know if it's a Mr., but it just sounds like it. Mr. Wonga. What is on the test? Nobody here on this meeting knows. Nobody here knows. But I can just advise that you guys understand the theory that you're dealing with. Don't cram. Understand those things in a way that you can put them in your own words. Read them and say them out in your own words. And then that simply means that you can write them in your own words. Cramming, you're going to write things that don't make sense by cramming, because theory is a lot. We all agree. And calculations are very small, which is going to be quite easy for you guys to work on. But understanding these things, I mean, you've seen with your tasks and your dummy test, the kind of marks that are allocated for stuff where you write with your own understanding. Just a tip. All right, Mr. Wonga. Anything else? Doesn't seem like it. Like I said, I'll be available on the platform, which I mean WhatsApp, between now and 10, right? Not to answer detailed questions, not to give the memo, right? I should say that we don't, that is not how it's done, right? We don't do that. There's no memo, unfortunately. Right, and don't send me questions and say, Mr. Fred, write this one for me, right? Because you have been doing that. You guys were saying you are fine. Follow-up questions, yeah, we'll be doing that. Discussions, new ideas on something, let's do that, right? Basically. Our meeting is going to end in like 2 minutes now. If you've got something else to say, you can just unmute yourself and say it.
How do you access recording?
How do you what? I couldn't hear that.
How do you access recordings?
How do you access recordings for this? You want the recording? Guys,
Yes.
do you want the recording? Hey. Okay, if it's that deep, I'll need to find a way to make it available. I'll post it and share the link, right? Is that okay for those who want the recording?
Yes.
Yes.
Okay, cool. But don't make this recording your main preparation stuff, right? Where you'll be listening to this recording the whole night in hope that you'll fly tomorrow, right? This is not it. That's a disclaimer. Yeah, we're just answering maybe the frequent concerns that you guys had before your test, right? Not to say this is the preparation for test. It's not. This is not preparation for test. This is sorting out your stuff before the test, right? All right, everyone, all the best with your test and prepare well. And tomorrow is the day. Huh? Good luck with the preparations there. If you have any concern, WhatsApp is open until 10. Right, I'm ending the meeting now.